A torus is it's basically two curves, not just two curves, two circles that revolve around each other. So let me, this is just a little tidbit at the beginning. We're not connected? Could you play around with the input? Oh, actually, it might help to actually plug it in. So if you were to draw a, are we working now? Yay. Okay. So if we were to draw a circle, and I were then to draw another circle relative to that circle, and I'm just going to draw it kind of in 3D at the moment. Actually, let's redo that. Just to make it easier for myself. So if I were to draw a circle relative to that circle, and then I were to redraw that circle at other points relative to this circle, then I do that infinitely, then what we would end up drawing is a torus. Okay? So the key thing here is the circles that sit on the inner circle, or whatever, that they have to be perpendicular to the circle. So if I were to test their rotation, they wouldn't be parallel to each other, because then you would create shit, yeah? So the fun thing about this is that if I were to draw any line sectioning my shape to the center of the inner circle, I would cut into the torus and generate a circle, okay? So there's a guaranteed circle if I cut like this. Another thing, if I cut through it, like as if you were to cut a bagel, like, do you know, everyone knows bagels? Yeah? So if I slice through it, through the plane of the table, I would generate two perfect circles. Like, they're circles, okay? And anywhere vertically, if I move that plane up and down, I will still generate circles. So this here is a circle, and that is a circle, and that is a circle, etc., etc. Okay? So there are some inherent things that we can know about geometry. So, for example, I know that if I collide two spheres together, like if I have them intersect, the interface between those two, this interface, will be a circle. So when I'm constructing, when I'm designing a roof that needs to be constructed, if I use a sphere as one part of the roof and a sphere as another, then I know that the beam that sits between those two spheres can be made of an arc, and that's much easier to construct than if I were to make some like fucked up curve. Cool? So we can't teach every single piece like rule here, but there are rules that like some fundamentals that exist in geometries. So the one thing that we are going to learn about are hyperbolic paraboloids. So a hyperbolic paraboloid can be generated by 4 points. I'm not going to draw it because I'm going to just erase it. You've seen me draw it for 4 weeks now, right? So the other way that we can generate hyperbolic paraboloids is using parabolas. So in one direction, topologically, you have a parabola, And in the other direction, so if I were to pick the 50% mark, right, you have a second parabola. So very similar to the torus, okay? We have one curve and another, and if I were to draw this curve infinitely along the second one, I would generate a hyperbolic paraboloid. But the only difference between this and the torus is that the parabola that you draw along the second parabola that you draw along the first one needs to be parallel. Okay, so it doesn't change angle as it moves along. Does that make sense? So, for example, when I move something in Grasshopper, it can only ever move. It won't ever change rotation, right? So the relationship between each of these is one that is of moving and not orienting and rotating, okay? It's just moving. Cool? So what that means is with a hyperbolic paraboloid, and this is the other interesting thing. Because you're doing that, this line here, if I were to pick another point on the parabola, such as this one, and we pick the same points all along here, that, if we create a parabola along those, it'll be the exact same parabola as this one, okay? So at any point, we can slice through this at the angle of the defined parabola, and we'll get a parabola, a perfect parabola, and we can also slice through that in the opposite direction, okay? Cool. Pretty straightforward? Yeah? We've got, have people been sick this week, tired? I've been sick. Nice, I like it. Comedic timing. Okay, so what we are going to do is we are going to generate a pavilion section using this method instead of the 4-point method. Okay? And to do so, we need to start defining some parent variables and child variables. Okay? So, and I'm not talking about variables that, rebel. We're not talking about teenage variables. They are child variables. So what's a one thing that parents and children do that you think it would be important in geometry? If your parents tell you to go to university and do a degree, what do?
Well, man, so
Huh?
I'm here, it's like that.
Yeah. Is that what they told you to do?
Repeatedly.
Yeah. If your parents, when you're younger, tell you don't put your hand in the boiling water, what do?
It's the same way that we extracted key inputs for clusters.
Kind of. Yeah. There's so basically, if I have a line and we have a point on that line, the point on that line is defined by the line, and the line is defined by the points that at the end. So in a way, the line is child to its parents, the points, and the resulting midpoint is child to the line, and therefore grandchild to those points. So if those points change, then it's forced to do what it's told to do, like a child. I think other people use a metaphor that's less authoritative. They basically go the parents create a child, and therefore the points create the line and then the line creates the midpoint, but I kind of like the you do what I tell you to do type of attitude. Because if we were to say, we know we want a midpoint between two points, right? And it has to be that point, right? Then if I were to then create the 2 points and create the line, does that satisfy? No. So in this scenario, what would we actually want the parent to be? If we know the point has to be there. I've drawn all 3 elements here. What would the parent be?
The point.
Yeah, the point. The point becomes the parent. And so, therefore, from that, we can draw a line. Or, the line could be there or there or there. And then from that, that determines where the start and end points go, because they have to satisfy that parent rule. Okay? So, if I had a circle, and the circle is where I need my columns of this pavilion to land, right? And maybe there's a few other little variables that we need to deal with. But if I've got this, and you know how we've generated we've got a midpoint and we've started to generate our surface, right? This becomes a parent guide, okay? And this becomes really important. So if I've got my parabola, and these things, they defy human basic understanding of geometry. It's curving in all directions and it's all fucked up. We quite like just flat things, right? We like to understand 2D flat things. So we've got this. Now, if I want this point here and this point here to be at the 0 plane, right? So if we're talking in 3D, we have X, Y, and Z of those points, and we want that point to be at Z, right? Then what does that end up making that point in relation to the rest of the parabola?
The origin.
Or the parent, right? It's a parent, yeah? So it was quite easy for me to do it with the point in the middle of 2 points, yeah? We can understand that. But how do we control a parabola from the parent that is a point on that parabola? Do you see where I'm going? Yeah? So if I said, okay, there's 2 points, right? I also want this point over here, its X, Y, and Z, to be 0. Z needs to be 0. Is that possible? It is actually. It's possible. How many points does a plane need? How many points can you draw that will guarantee you a plane? Minimum number of points. 3, right? So I could draw a plane across those 3, and their Z will all be 0, right? So I just threw a little trick question there, right? But if I also drew this one, right? And we want all their points to be Z to be 0, then we can't, right? It's impossible. So
If it's flat, then surely.
if it's what?
If you put it laid down.
Which one?
your
The
plane.
shape, the plane.
Yeah, why can't Z be 0?
Look, there's
It's not on this situation.
yeah. So let's now assume that we're using XY plane, right? And it's relatively, we're thinking that is up.
Yeah, okay.
Okay, so what we need to start doing is thinking of this in these terms. So these 2 points, we need to also control their x, y values, not just their z's. Their x and y value needs to be the x and y values of like these 2 points, yeah? And they need to end up making a parabola. So this is one of the more difficult concepts to get across. Okay, so are we all clear with the parent and child relationship? Okay, so if I were to, let's pseudocode it. It's always the best thing to do. Have you guys been enjoying the pseudocodes? Have they been helping? They're probably more useful than actual like grasshopper coding, apart from actually like to doing the assignment. Like if I just explain grasshopper, it would make less sense. Yeah. Okay, so just remember, what do we need to make that type of hyperbolic paraboloid? What did I need? 2 things. Just what 2 curve type geometries do I need to generate a hyperbolic paraboloid? Say it. Don't conduct it. We need, no, we're making a hyperbolic paraboloid. What do we need to make it? So what do we need to make a line? How many points? 3 points, 2 points. Okay, what do we need to make a hyperbolic paraboloid? I just drew it.
2 points. 3 points.
Not points. 2 parabolas. Yeah, do you remember? 2 parabolas, okay? We need 2 parabolas. I'm going to throw in a little guide for you guys. All I need to generate a parabola is 3 points, okay? I need 3 points to generate a parabola, okay? Done. So, if all I need to generate a parabola is 3 points, and all I need to make a hyperbolic paraboloid is 2 parabolas, we can extrapolate that we only need 6 points in a system to generate it, okay? So, assume we're going to start with 2. We're going to start with these 2, and I'm going to work on them over here. So here's my 2 points in 3D, yeah? Let's start making this work, okay? So what should I do first? And if no one, this is one of the ones where I'm going to give you the answers quickly. Huh? I like it. Okay, let's find the midpoint, yeah? Then what? No, because if I connect it, I get a line. That's not a parabola. Brrr. Move it? Let's move it up. Okay, so we're going to move that up and then make a parabola of those 3 points. No, we've got 3 points now. So what can I do?
Join the points.
I can join the points parabolically. Yeah? Whoop. Parabola. Okay. Now, this parabola is satisfying something already. It's already going through our points, yeah, on our circle. So no matter what, as long as we use this parabola at that position, it will always go through those 2 points. Cool? Okay. So if I would, okay, let's keep going. Next, let's just go back to the circle. We've got this point here. If I draw that in plan, it's there, right? And I've also got a center point. Yeah? So let's start thinking. What do I need to make the second parabola?
5 find the midpoint between the center point and money.
So this is the thing that Candela did differently to what you did, what you're talking about. So what Joe's saying is that these 2 points here are effectively the equivalent of these 2 points. Yeah? But what Candela did was he said, okay, this point here and is actually an endpoint. This is the midpoint, and this point over here will be the opposite. Okay? So what we're going to do is we're going to find the mirror of our point to the center on the opposite side. So if I were to draw this in 3D, we would end up getting something like so. Yeah? And is there anything we want to do? Like we probably want to move that up, yeah? So we'll move this up. And we've got 3 points. So what can we do with 3 points?
Make a parabolic line.
Yeah, generate a parabolic connection between them. Cool. Now, what is the relationship between this parabola and this one?
Which one?
There's 2 parabolas. Let's call parabola A and B. Do they touch?
Yeah.
Right. So they're touching, and at what point do they touch?
The end point.
This point here, yeah, the end point for point B, for line B, or the midpoint for parabola A, right? So we know they touch, yeah? So then what else do I need to do to generate a hyperbolic paraboloid? What's the last thing?
Make a surface.
Yes, but there's a lot of different ways to make surfaces, okay? So what, if I were to, has everyone here lofted? You've used loft, yeah? So what does loft need? It needs more than one curve to generate, huh? Yeah, it needs a series of curves to generate that surface, okay? So let's just think that way. What do we need now to finish this off and actually generate a surface?
You need to connect the 2 bottom points so on parabola A, you've got the 2 points at the bottom which aren't connected to anything.
That's fine. We're making an open surface. So that's cool. That's not what I'm talking about.
Replicate A across B.
Yes. And how do I replicate that?
If you like reparameterize the curve between 1 and 0 and number slider.
Yeah, but what geometric function are you doing? No. So what geometric transformation are we doing?
You're scaling it down.
No, scale is totally the wrong answer. Okay? Be really careful with the word scale. Okay, scaling is making something bigger and smaller from a center point. Okay? So what are we going to do to this curve to get it to the other parts of it? What are we doing to A to get it along B? We're moving it. Yeah? We're not rotating it, we're not orienting it, we're moving it. Okay? So what we're going to do is we're going to evenly divide B, and then we're going to move A from its origin point to all of the new points along B. Yeah? And then we loft. So what does this satisfy? If I draw that surface now, it's going to look like this. Yeah? If I cut that surface from this point like so, then I guarantee you that these 2 points at where we're cutting it to are going to touch the ground. Yeah? And that's because we've set that as the parent. Yeah? So what we're going to do is then we're also going to cut this shape using a plane but the plane is not going to be vertical, okay? So if I were to cut it vertically, what type of shape would I generate? A parabola? Yep. And if I cut it vertically in plan, it's just going to look like this, yeah? But if I cut it on an angle, what type of shape am I going to generate?
Hyperbolic paraboloid.
No, we've already, this is the we're cutting a hyperbolic paraboloid. So, okay, now this, I just want you to think a bit critically, okay? So if I have a cylinder and I cut it perpendicular to the surface, what do I generate? No. What shape? Like if it was made of glass or it was made of smoke and I had a laser plane cutting through it, what would the laser plane shape create? A circle. Okay. If I did the same thing but cut it at a weird angle, but you know didn't ever hit the end, what shape would I generate? An ellipse. Okay. If I had a cone and did the same thing, what would I generate? And if I did the same thing in the other in a weird fucked up direction, what would I get? No. You get a fucked up shape, right? Let's keep that as like the official term, but only in this room, okay? We get an irregular geometry, yeah? So if I were to cut a hyperbolic paraboloid perpendicular to its topology, I would get a parabola. If I were to cut it the other direction, what would I get? No, you get a parabola. No, the opposite, 90 degrees to it, right? But if I were to cut it at a weird angle, you would get a fucked up shape, right? You're just one step ahead. Yeah, too soon, right? But the point being that in doing so, when you cut it, it's going to generate those shapes that I think a few of you have been trying to emulate, because you can see them in your candela form, but you haven't been able to produce that, right? So what we're doing is we're over-generating our surface, like we're generating beyond what we need, and then we're going to trim it down to the shape that we want. Cool? And in doing so, by setting out these parent variables, we're good. So, there is two ways to make a parabola. No, there's not. There's only one way to make a parabola in Grasshopper, and it actually involves writing maths. Fuck that, okay? We're not going to do that. Because can you remember how to write the actual formula of a parabola? We're not going to do that, okay? Because in doing so, how do we, then if I go, okay, remember parabolic formulas? Now I want you to make sure that it goes through these 3 points in 3D space. You'd be like, fuck you, Andrew. You're a fucking dick. So, Grasshopper has a way of creating a fairly close to parabola, and I'm okay with that, okay? Even though we're talking today as if parabolas are fucking awesome, in construction, they're shit, okay? We don't use them very much. They are expensive. I don't understand why they're expensive, but they are. Does anyone know how beams are rolled? Like, how do you create a curved beam? So it goes through a machine, and that machine basically stretches one side and squishes the other as it rolls through. There's a wheel, and the wheel effectively grabs onto it and rolls it. And when you put something into that machine, there's a little console that you go 20 meter radius, let's say. And you don't go halfway through and go, okay, now 19.2, now 15.3, now, but like to generate a parabola, you have to effectively get that machine to constantly change the radius that it's trying to achieve to actually be able to generate it. I think there must be a CNC way of doing that, but apparently there's not enough designers in the world that actually want this as an outcome to warrant that machine actually existing commercially. So even though it sounds like I'm obsessed with parabolas, seeing as everything we're doing is a hyperbolic parabola, I rarely use parabolas. Rarely. Okay. So we have pseudocoded. Let's do it. Let's actually code. Let's just make sure. I always forget to put this in airplane mode. Wow, that took half an hour. I feel like I explained that. That wasn't so hard, was it? No, okay, good. Okie dokie. So what we're going to do is we're going to start from scratch. And I'm probably not going to explain too much from the beginning, but we're going to create a circle. This time we don't need to create an inner circle or an outer circle, we just need one circle. And with that circle, yep, that's still recording, excellent. With that circle, we're just going to work on one section. That's it, okay? Okay, so let's generate a point. Today we're just going to generate it at 0, or we're going to go grab the construct XYZ point. Far out, I still can't, it's very difficult for me to actually see this on the screen, let alone I can imagine it's very difficult for you to see, right? It's quite hard, right? Yeah. I think it comes down to if someone asks me, hey, if you could use a TV screen at work for your monitor, would you? And I would say no. That's kind of what you guys have to do. Okay, and we're going to make a circle. Let's do it. And we're going to create a radius. Let's make that 300. I think was a reasonable size for this. Or it could be smaller. There we go. We're going to divide the curve. And that can be any number of divisions. So we'll go, let's say 2 is less than 20. Actually, we can't actually make it 2. Let's at least make it 4. And we're good. Okay. What is something that's going to make this a lot easier to work with in future assignments is actually rotating this a bit. So if I just quickly grab the first 2 points of our divide curve, what that's going to do is it's going to basically set us up to be generating our segment on this wedge here. But in future assignments, it's going to be much better for us if this center line of our topology, this one here, is in the X or Y direction. Okay, so one easy way to actually achieve that is if we use a dispatch of our divide curve, and we get rid of the first points, so we'll get rid of A, so we'll just use B. And instead of using I plus 1, we use I and minus 1. That somehow fucked that up. And one more thing. We just also need to make sure that the expression in our n is set times 2. So we'll go x times 2. Sorry about that. So what that does then is it guarantees us...
Is that x times 2, is that right?
Yeah, on the n. X times 2. So what that does, guarantees us a our segment here is going to align along the x direction, which is going to make future assignments much easier, okay? Does that make sense? Okay, has nothing to do with today. It has everything to do with making every other assignment breezy. We skip 10 minutes every lesson from now on because of this one thing. Cool? So has everyone got I and minus 1? Excellent. Pardon? You got to hide it. By the way, guys, even though I haven't seen any of your assignments, you're doing a really good job, okay? I can tell you're doing a good job. The fact that you're following along, and do you know how long it took me to explain this week 2? This took me forever to explain week 2, remember? Now, I could go make a circle and divide it, and you guys are like, cool, I'll go make a circle and divide it, that's easy. Cool? Okay. So, we've got, I don't know why I did that, but okay. Okay, so we've got our 2 points. Now, Grasshopper has a cheats way of making parabolas. It doesn't make a perfect parabola, but it's close enough. And this is why I said it doesn't really matter, because it's not like we use perfect parabolas in construction anyway. So, we're good, okay? We're gonna make a cheats parabola. So, to do so, how many points did I say we needed in the pseudocode? 3. Okay. Now, the cheats way of making a parabola in Grasshopper actually doesn't. It's a bit counterintuitive. What it requires is 3 points, just as I mentioned. But if I want to achieve a parabola that goes through these 3 points, I'll bring them into actual Grasshopper. These 3, and I use this method, the curve, the way that we're generating the curve is it's actually a pure NURBS curve, which means the alternating points are going to create a control point, and then a weighted point, and then another control point. So what that means is if I draw a circle and I draw its control point structure, so if I cheats way bounding box, so you can see this would be a control point. Our curve goes through that. And then this point here is a weight for the curve. And there is our second control point, and here is a weight. So if I actually look at this curve now, and if I just take this out, see its control points and its weights? So there's a control point, and there is a weight, and the weight doesn't actually define where the curve goes through the, in terms of its shape, okay? Which means if I then try and create a curve out of this shape, it doesn't actually go through that point, right? And if we want this point here to be the defining point of where it is on the parabola, because remember, in parabola B, that point there is actually the point that the parabolas need to intersect. So, and look, this point here is actually where the parabola goes through. The rule that we need to follow is the control point for this purely needs to be double the distance for that parabola to go through that point, okay? Quick, cheats little rule there, okay? You'll probably never use it ever again in construction because we never work with parabolas, but there you go. I learnt this because of this class. So, if we've got our 2 points, what did we do first? We had 2 points. What was step number 2? What's your name again? Yeah. Woody, that's right. Woody, what was the next step? You were the one who said it. We had 2 points. So we've got our 2 points here. What did we do? Remember we went, okay, let's go to 3D. What was the next step? Come on. Was it a fluke that you got the right answer? We're going to generate a parabola between these 2 points. What do we need to make that parabola? It's a very, everyone should be able to answer this now. What do we need to make a parabola? So what's the next thing we need to do?
Draw a line across the two.
Get a midpoint. Okay, so let's get a midpoint. Now, today we're going to do a whole bunch of cheating. I'm going to show you some shortcuts. Okay? So one way that we would do this is you could draw a line between the two and then get the 50% way along that line. That's a really cool way of doing it. I like that way. But because you already know how to do that, I'm going to show you a nice little cheats way. If you average 2 numbers, you get the midway between them, yeah? If you can actually do that to things other than numbers. If you average 2 points, you get the midpoint between those 2 points. Gotta like that. So if I plug 2 points into average, I will get the average of those 2 points. Nice. So what that can do in the future, for future reference, you can plug more than just 2 points in. You can plug in 100 points and it'll give you the average point. So that might be useful. Who knows? Okay? There's a nice little trick there. Cool? Okay, so we've got our midpoint. What else? What next?
Gonna move the midpoint up.
We're going to move it up. Okay, so if we move it up, so I'm going to use a Z vector. I've talked to you guys about this, right? It's so hard. So I teach three groups of Grasshopper learners simultaneously, throughout the week. And it gets harder and harder to track what I've taught them. So if it sounds like I'm getting senile being like, have I shown you guys how to do this? When it was only just a week, it's probably because I'm just getting muddled, okay? Or senile, maybe. Okay, so unit Z, we're gonna plug that in and we're gonna grab a slider. And we'll make that slider go between 0 and, let's say 200. Now, we've got a problem, because if I merge these guys, If I merge point -1, the moved midpoint, and the I of the index, and I create a NURBS curve, then we are in a problem, right? Because we haven't, it's not achieving what we want. Now, what's one way out of this? One way out is we can just put up with whatever Grasshopper gives us, and we'll just find the midpoint of this curve and then just use that as the point to generate the next parabola. But we're not going to put up with Grasshopper telling us what to do, okay? Because we want this point here to actually be a parent. That point is a parent point, not a child point. It's not going to be a child of that parabola, okay? So I've moved this, but that's not actually, this isn't the point that we want to use. We want to use a second point, or a fourth, I guess. And that point is going to be how much higher up than the actual parent point? Twice, which means if I just right-click the F input of that second unit Z and times that by 2, that will put a double-heighted point into our system, and we're going to replace D2 in our merge with that point instead. Too fast. Guess what? It's literally the exact same function. Generally, if you see, like if you're trolling around a script and you see these like little expressions on things, my rule of thumb is I generally only do super simple functions in them, super simple expressions. So they're generally just going to be -x, x times a number, or 1 minus x. Yeah.
Just in my expression, they have to be times 2.
Yeah. Yeah.
The curves have to
Yeah, dude, look. Even though you've times it by 2, have you actually plugged it in?
Oh, okay.
How's everyone going? We're all good?
No, mine's not going to the second point.
Is that because you haven't plugged it in?
No, it's plugged in.
Are you sure?
Yeah.
It's not meant to go to the second point. It's meant to go to the first point. Like, what do you mean? It's not going up to here?
Yeah.
Huh?
Yeah, it's not doubled.
Are you sure you've got x times 2 and it's plugged into the move?
Yeah.
Okay. Yeah, it's doing what you need.
Oh, I thought I had to go up to that one.
No.
Oh.
It can't, right? That is the guy. That's the weight, and that's the one we want it to hit.
Gotcha.
Yeah. Cool. Jeez. No, it's not working. It is working. Actually, that's one of the easiest. I love problems like that where people are like, my script doesn't work. It's like, actually, it's working. Okay, so we're good. We've made our first parabola. Yes.
Last week when we did the elliptical cutouts to make the living here,
Yes.
you did like connect curve and then you offset the 1 point on an axis away from those 2 points. Why didn't we just replicate that? Because that would still give us a parabola.
No. An ellipse is not a parabola.
That would get like the curved edges.
But we didn't use parabolas last week. We used arcs. They're very different, and they require less effort. Arcs are much simpler, much more easy things to deal with than parabolas. So whenever I have a chance to use, like if someone said to me, go make an oval, a cricket oval, right? And everyone in their mind thinks cricket ovals are ellipses. They're not. They're actually generally 6 arcs made to look like an ellipse. There's a simplified ellipse down into arcs. Because when you generate a structural grid or like a planning grid off that curve into the stadium, you kind of want to standardize the angles between each of the grid lines. Like if you had every grid line was different and therefore like all your structural components had to be different lengths, like it starts to get more and more and more expensive just because you've used an ellipse over an arc. And hence, like, we used arcs last week because we only need 3 points and it goes through those 3 points and it's clean, it's nice, yeah. If this class teaches you anything, is just keep as far away from parabolas as you can. Okay, so why did you ask?
We've pretty much done the same thing.
No, we haven't. No, we've had to generate 2 pieces of geometry, like 2 points, to make a parabola, whilst last week we only had to make 1. Yeah? And we don't want to offset, we know, the reason we offset last week was the direction of each line was different. They were all pointing in different directions, so we couldn't just say, move in X, right? We had to say move relative to the curve. But with this one, we know that we only need to move up. Cool? Okay, so we're starting to see we've got our first parabola, okay? What do we need next? Second parabola. Okay, so we've already got 1 point for that second parabola. To generate the other point, all we have to do is get this same point on the opposite side of the circle. I'm going to show you a really bad way of doing this because it's quick and you haven't used it yet, this process, okay? And that is, we are going to mirror that point to the other side. So there is a mirror component. It works exactly as you would expect. It mirrors, it takes geometry, it takes a plane, and so the plane we are going to use is XZ, the XZ plane, and we are going to mirror that point to the other side. Sorry, did I say XZ? I meant YZ. My eyes chose the right thing, but my mouth said the wrong.
Can I just ask why we've taken that point, not the other point?
Because the way this technique generates parabolas is the start and end point are where the actual curve goes to, but the midpoint has to be double that for it to work. Cool? Cool. Okay, so can anyone explain to me why what I've done was a bit shit? What I just did now when I mirrored?
Because when we try and make the actual building, you make the Castella's building without mirrors going both ways.
Yeah, I think you understand what the issue is, but you're just not articulating it.
Kind of like if we change a part of the model, it'll then change on the other side, but it could go.
So the main problem is, if this script somehow were to rotate, even by less than a degree, we've just fucked it up. So we've made this have to be drawn at 0, and it has to be aligned to X. If it's not aligned to X, then the opposite side of this line is going to be somewhere else on the curve, right? So we've set a very rigid thing for ourselves. I'm just like, it's okay at the moment, but one day you're going to realize like there are reasons why this is bad, okay? And I'm just pointing that out to you now. So we're doing something bad, but it works, okay? It's the wrong way to do it, but we get the same result. Okay. So what we can do is we can actually probably work to the same method that we've just worked here. So what I'm going to do is I'll just grab a point parameter and plug that into the mirror just so that we know we're working with these 2 points. All we have to do now is work with this same method. We can effectively grab the average and use that to find the midpoint. We can grab the moves and we can use them to move that point. But too fast? I'm just copying and pasting, mate. I'm literally copied and pasted what we've just done. So we're going to average the 2 points. What? Okay, fine. I'll slow down. I'm going to copy the average. This is what's proving to me that you're just following along and not actually understanding. We're going to copy the average and we're going to plug our point on the parabola and its mirrored companion, generating the midpoint. Baptiste! Hey man, how you doing?
Hey, how you going?
Good.
Is this the
This is-
code 1, 2?
No, this is Beil 0015, which is a copy of code 1150.
Oh, sorry.
So these guys are non-code students
Dang.
learning 1150, and this is a very different 1150 to what you did.
Yeah? What's different?
Christina's in charge.
Right. I heard that there was a lot of,
Well, you've got Christina for another class.
yeah.
Imagine that, but applied to 1150. This is being recorded.
Okay,
Okay.
cool. Alright, well, have fun.
You too, man. See you around.
Yeah.
Cool. Okay. So, is everyone at where we're at? Everyone's there? It's literally what we've done here, but with a point and a mirror point instead of 2 list itemed points. Yeah? Straightforward, yeah? Then all we have to do is move this point. We just need to move it. So why not just copy this? We'll copy this section here and move the new averaged point. But we want to change something. Instead of moving it up, what do we want to do? We could actually move it up. But instead we want to move it down. Okay? So there's 2 ways of doing that. We could either make this slider go to a negative number, or we could just right-click into the expressions of both these sliders and go minus x. And in the one that was times 2, instead of typing x times 2, we'll just type minus x times 2. And now we can move these guys into a much nicer.
You put that into both the UNZ guys?
I've put the top one into the top one and the bottom one into the bottom one.
Yeah, because that's pretty fine.
Do you understand why I've done this? all it does is just point the z direction in the opposite direction. Yeah? The expressions are really cool little things that help us basically, instead of like forcing the slider to be the exact number that it needs, you can force like a rule to be applied to that number before it goes into the system. It's how I generate centers. So if I need a center line and I offset two things, I set the offset distance to be half the number that I want to offset, and the other one being negative half. And that way, the number that I put in is the width between the two, and they move on that center. Cool? Okay. Are we at this point? We've got an average, we've got two moved. One is the one we're going to use to control it, and the other one is actually the point that line's going to go through, and we've got the point and its mirror. Yeah? That means we can just copy the merge and plug our start point into the start, D1, the mirrored point into D3, and the doubly moved point into D2, generating a nice little cheats parabola, Parabola B.
Could you repeat that?
Yep,
Could you scroll out to 20?
sure. All I did was I copied this down, and remember, we're going to use this point, the mirrored point, and the doubly moved point as the 3 points that create the merged parabola. Did you do it, Joseph?
I did do it.
Good job, man. I saw someone get super excited about Grasshopper the other day. They were like, I think they'd been trying to work something out for like 10 minutes, and then they just connected one wire, and it worked, like it just clicked into place and worked, and they were like, yeah! There's work in this, guys. Like, I get paid to do this. Like, it's not just fucked up, like, curved geometry. Like, there's actually work in this. This is...
Even in parabolas.
Huh?
Even in parabolas. Even in these.
This is teaching you way more than just parabolas. You're learning a new way of thinking. We're reprogramming you right now. That's what we're doing. We're teaching you guys how to think a different way. Actually, and for some of you, in a new way, like you haven't really been drawing stuff prior to this. Okay, so we've got two parabolas. We're there. Look, we made it. We're almost there, right? What do we have to do? We just have to create a surface along one of those parabolas. So we just need to effectively move one of these parabolas, let's say parabola A, along parabola B in, let's say, even divisions, and we're going to generate a nice surface. Cool? So let's do it. Yeah, if you say so. I'm guessing it was that type of laugh. Like, it's just that simple. Yeah. Okay, so we've got parabola B. Let's divide that. That gives us the points that we need to move to. Okay?
Working
Huh? We're just using divide curve.
working on B.
We're working on B. You could actually work on A. It works both ways. It works both ways. Serious. I'm being serious here, guys. This is some cool things about geometry. If you do it one way, you can literally reverse it, and it'll work the other way. So, for example, no, the torus isn't a good example. Okay, that's a bad example. Where are we? Where's my mouse? Okay, so we divide our curve. Now, what do I need to move? What do I need to make a move?
The first parabola A.
Okay, so let's look at move. What do we need to make something move?
A direction or a vector.
I like that second word. We need a vector, okay? So, and we also need geometry to move, okay? So we know what geometry we want to move. It's this cheap parabola. Now, how do we generate vectors? What are some ways to generate a vector?
2 points.
2 points, right. So if we have 1 point, we know where 1 point is. Ugh, what's going on here?
I've done that to mine as well.
Ah, okay. Let's just forget the move. Okay, so we've got one point. We know that point. It is this point, right? The point that the parabola goes through, yeah? And we have a list of points that we want that parabola to move to. So if I grab our vector 2 point and I plug my point the parabola travels through and I plug in the points that I've divided parabola B to, what that will do, just to remind you guys about lists. Okay. Have I taught you about this? If I've lists in Grasshopper, whoop. If I have list A and list B, you can tell I've been using this whiteboard, right? It's got little crosses on it. I've got list A and list B, so here's 3 points in list A and here's 3 points in list B, yeah? If I were to draw lines between them, I would get this, you would assume, yeah? I've explained this, right?
Yeah, it goes the other way.
If I shift them.
Oh.
Okay, so here's a new little thing I need to explain about Grasshopper. If Grasshopper has 2 lists, and one list is shorter than the other, let's say list A and list B, list A has 2 and list B has 3. So in theory, 0 connects to 0, then 1 connects to 1. What do you think happens to 2 in this list?
We go back to 0.
No. Try the other direction. It just repeats the last one in the whichever is the shorter list. Okay? And we've probably already seen this, I just haven't explained it. Okay? So, what that means is, if we've got a list that only has one item, and we have a list with multiple items, then it's going to repeat the one item over and over again, therefore creating this. Cool? We've already done this, I just haven't really explained it. Does that make sense? Okay? Cool. So if we've got one item and we create and we use a list as the other, what we're actually going to do is generate a number of vectors that go from that starting point to each of these points on the curve. Which means if I use my transform to move that using that vector, that will transform our parabolas along the curve.
What goes into the top of transform? Sorry.
Highlight the G of transform. You can answer your own questions with Grasshopper.
So like
Yeah,
My parabolas extend below the ground.
that's fine. Look, so do mine.
Oh,
The thing is, if I cut an object from this point to this point, I'm guaranteed the parabola will touch the ground at that point. And only that point along that parabola. Anywhere else, apart from its opposite, but if I go anywhere else along that, it's not going to touch the ground. So we know that it's going to touch the ground now.
Is your nerve curve still connected to the merge?
The move? Yeah. We're merging.
Yeah, so that's there.
Yeah.
Oh, right, got you.
Yeah.
No, that's not right.
Huh?
That's not right, I thought that curve.
Hey man, you're not using the right transform.
Oh, we're not? Oh, yeah, that'll do it.
No, we want move.
Okay.
So remember that was in the right,
Yeah.
and
So that goes to the...
yeah, and then that needs to go. The vectors need to go into the vector.
There
Yep,
we go.
done.
Okay. We're not worried about that.
All good, huh?
We're not worried about that.
About what? Nope, no, don't worry about that. No, we're all good. Yeah. Ah. Come over here. That's exactly what I said would be a problem.
These three came out of
What? How do you get spacebar? It's not fair.
I. So your face is
You've just used the wrong. Yeah. That's okay.
What thickness are you doing? I'll probably do quite thick. Yeah, because I did it for you.
Ta-da! No problem. Okie dokie. We're looking pretty good, right? Oh, assuming that you can see through the whiteboard, yeah?
See through the whiteboard?
Yeah, like, remember the shape that we drew?
Yeah.
It's looking pretty close to this, right?
Yeah.
Yeah? Okay, so we're almost done. We can basically loft those curves now to generate that surface. So we have a slight issue. If I were to start making my candela shape now, like relative to some of the pavilions, yeah? If I were to start my little section off and go to these points, the result should have like a little section that might come out like that, right? But my surface doesn't actually go that far. Yeah? So what we're going to do is we're just going to make sure that our surface goes beyond the bounds that we've drawn. And to do so, we just need to take the curve, this curve, parabola B, and extend it longer than what we've drawn. Okay? And so what we'll do is we're just going to cheat. We're going to use extend curve. There are mathematical ways to do this properly, but that would take literally the rest of the class to do this. So we're going to extend the curve. We're going to grab a slider. We're going to plug in a number. Let's make it go all the way up to 300 if we really need it to. And that's going to plug into the L0 and the L1 of our slider. And if I just extend that out right now, what is that giving me? What is it doing?
Just taking the curve around the shape.
It's creating a tangential straight line at the end, okay? And we don't want that. So what we can see on the T is there are, if we mouse over it, you can see if I put 0 into that, it's going to give us a line type extension. If I put in 1, it's going to give us an arc. And if I put in 2, it's going to give us a smooth. So what we need to do is generate a number slider that goes from from 0 to 2. And I'm going to let you guys have a guess as to what choice you want to use. You just showed me a number that isn't actually on the yeah. You're like, it's definitely this number. Yes, 2.
That's what I meant.
Yeah, I could. You're like the third one. Cool. So we want the third one, number 2, smooth. And so if we then use that in our divide curve, that is going to generate a much longer hyperbolic paraboloid, which is then we can use to do that extension for that geometry. Huh?
Extension component happening.
Yeah, amp up the number, like not that. Yeah, that one. Yep, make it bigger.
Oh.
So if we were to start, we use the word cut, that's the right word.
It's the right word.
Oh, good. If we were to cut this, we'd have to do it in Rhino.
No, we're going to do it in
We're
Grasshopper.
going to grasshopper.
Yep, let's do it. Okay, so we are going to do this cut in a way that is sensible. What we're going to do is cut our objects on the end first, and then we're going to cut it to make a wedge. Okay, so first we're going to slice it on the end, and then slice it along the wedge. Okay, because slicing it along the wedge requires just a 2D wedge drawn in plan, and we're going to project up and slice using a projection. But the slicing on the end requires a plane in 3D. So we're going to do the more complex one first, because it's more complex, basically. Okay, so we're looking pretty good, aren't we? You'd never think that you would be able to make something this parametric 3 weeks ago, yeah? Especially something this mathematically complicated to most people. Cool, okay, so we need to generate a plane. So, can anyone give me a way to define a plane? How many? I've spoken a few times about this. So 3 what? Right, that's a good one. I like that one. 3 points. That's a good answer. What else is there? What if you think about how planes are represented? What are the 3 things that are always represented when we represent planes? There's 2 axes normally, and then an origin. Okay, so have I shown you guys how to make planes out of anything yet? How do we want to do it? Shall we do it with vectors and an origin, or should we do it with... I think we should. We'll do vectors with an origin. Okay? Let's do that. So there's so many ways to make planes. If we go to the vector tab and we look under plane, see all those plane functions? Most of them are the various different ways Grasshopper is allowing you to make planes. There's actually more ways to make planes than just this. But yeah, there's a whole bunch in there. Cool. So the one that we want is the vanilla one, construct plane. And so what that does is assume that you have an origin, an X direction, and a Y direction. Okay? What we're going to do, just before we actually do it, just to explain, we are going to generate a plane, a vertical plane, that goes between these 2 points and then up, because it's vertical, and we're going to then rotate it to then slice this geometry. Okay? So, if we're going to create a vertical plane between those 2 points, what would one of the vectors be that define the plane?
These are 2 points that we create.
Yep. And then what would be the other? Just remember what type of plane I said.
The midpoint, so where the
No, vector. I didn't say point, I said vector. So if I generate a vector between these 2 points, instead of drawing a vector, I'll just draw a line. So we've got our 2 points on our circle, yeah? If we generate a vector between these two, assuming the line is a vector, that's one vector. What would the other vector be? And remember, I said something specific about this plane.
It's the one that we've moved out.
No.
No.
It's a very simple vector. Any vertical surface in reality will have this vector. Assuming Earth is flat. Assuming. Every time we model a building on a computer, we work in warped space. We take the Earth and make it flat. Yeah? Say it. You're one letter away from being correct.
Who?
Z. Z, up.
Oh, I thought you were saying Y as in Z. What W?
Up, right? If I make a vertical plane, the one of the vectors is always going to be Z. Yeah? Does that make sense? Cool. Okay, so let's make a vertical plane. Let's grab a 2-point vector. Let's get the 2 points that make up the first vector, and let's go grab a Z vector as the second one. And we're going to use that in the construct plane.
You grab those out of the side?
Which ones? Oh, yeah. These are, we're just using these two. Okay, we're going to use these two vectors, and we need an origin. Does anyone want to have a go at choosing an origin? It's got to be probably one of these 2 points, so therefore, whichever one you want to use is fine, okay? I'm going to use -1, but you can use I if you really want. And if I preview that, that's going to generate a nice little vertical plane. Oh, blimey.
I know, I said, oh, it's tiny.
Oh, it's tiny. Okay, so if, guys, because planes are infinite, Grasshopper represents them with a size, and you can change the size of the way planes are displayed if you go to display and then under preview plane size, set that to a reasonable scale. You can imagine I work on urban planning scripts, and I also work on scripts that design chairs. My urban planning plane sizes are going to be different size to the ones I use for my chairs.
So what's the reasonable size of it?
Well, what size model are you working on right now? How big is it in real life? This big?
Probably.
Yeah? So we would want planes maybe displayed about this big. So 100 mil? All good? Sweet. Okay, now we need to rotate this plane because we don't want to cut through this thing vertically. So if we just go check out our transforms, there's a few ways to rotate. There's rotate, there's rotate 3D, rotate axis, and rotate direction. Now I really like rotate, and the reason I'm going to show you rotate is that it requires you to actually use a plane, okay, to rotate on. So if I were to take this Pepsi Max bottle and we play spin the bottle, yeah, I'm using the table as effectively a plane that is rotating on, yeah, and the center of the origin is effectively where it's rotating. So the reason we're going to use rotate is it's just going to it's going to force us to do another example of generating a plane, okay? So there are other ways of making planes, and there is one that is very rough, and it's not the most, it's not a plane that you can control very well, and it is generating a plane by its normal, okay? Everyone's familiar with normal? Not like, I feel like I say this joke all the time, not like I'm weird and you're normal, like, do I need to explain what normal means? Yes? Okay. Everyone knows what perpendicular is? Okay, so something that is perpendicular can only be perpendicular in a 2D environment, okay? So on a square, that relationship is perpendicular, yeah? In 3D, if you have a shape, then there is a point on a surface where, in all directions, at that exact point, the line coming off of that, or the direction coming off of that, is 90 degrees, 360 degrees all the way around. That line is called normal. Okay? So, if we think of a plane in 3D, with the x and the y, what does that mean about the z? What is z relative to that plane? It's normal, yeah. Excellent. So, what this is saying is, if you have an origin and you define a normal, so for example, if I define the normal as the vector that I've used between these 2 points, so this 2-point vector here, what that'll do is generate a plane that is using that z vector as a normal. Cool? Now the reason I'm saying that this one is less controllable is you have no control over which way the x and the y are pointing on that plane. So that plane could be rotated in any direction, and if you need those x and y planes to be pointing in a very specific direction, this doesn't let you control that. But all we're doing is using this to rotate, so it doesn't matter, okay? So we're going to then place this plane as our rotation plane. We're going to rotate our constructed plane, and we're going to use a number to rotate. So what I'm going to do is put in minus 90 to 90 in my slider. So we can go either direction, minus 90 to 90. And have I explained this? Almost every single rotational thing in Grasshopper actually uses radians, because radians are actually the mathematically clean way about talking about angles. But all of you probably don't think in radians at all. Like, no, like, can anyone think in radians? No? Okay, good. That's good. You're all normal. Yeah. Just to pull back on that. Yeah, exactly. So if I plug this into the angle, it's not actually going to give us 90 degrees. It's going to give us 90 radians. So what we need to do is right-click the A, and you can select degrees there, and that will then force that component to think in degrees. So then, if I just hide these and slide this guy up and down, we can see that is now rotating that plane on the other plane. I can make it go in either direction because my angle slider is going from negative 90 to 90.
Mine's still sort of rotating around the center point of that plane.
That's fun. What do you mean? Are you using... Is it rotating... What do you mean?
So, can you just put your view on...
So I've got... This is the plane that we're rotating, right? And then we're rotating it on this plane. So you can see it uses that like the table. Cool. Excellent. Okay, so let's do some intersections. So we've got a plane and we've got a surface that we are working with. Let's just make that less than that. Yep. So we haven't done any intersecting. Oh, we have. Remember we used this component in intersect called curve self, and it worked out. It told us whether or not a curve was intersecting itself. So what answer did that give us? If a curve intersects itself, like so. If I ask it to intersect, find where it intersects, what would the result be? If I intersect two curves, where can they, or two lines, let's say, how do you define where they intersect? As a point, yeah? Okay, so if I intersect two 3D geometries, such as a plane and a surface, what is the outcome going to be? Or a curve, yeah. A line or a curve. So the interesting thing about intersections in Grasshopper is you can't just tell two things to just intersect. You need to know exactly what they are when they intersect. So what are we, like if I intersect these two objects, what am I intersecting?
Plane and the geometry.
But what type of geometry is it? Because technically, planes are geometry. So, loft is a bad word. It is a loft, you're right. But let's think of what is it? Like, what category does it fit in? It's a B-rep or a surface, okay? So we are intersecting a plane and a surface. And the way intersect is divided in categories ignore region and shape at the moment. We are looking at either mathematical or physical. So all the mathematical intersections in Grasshopper assume that one of the elements that are being used, or at least one, is a mathematical type geometry, so therefore it could be infinite. So planes are infinite, okay? I know you probably don't think about it too much, but lines are infinite. Lines can go on forever. We're just seeing a small segment of them when we look at them, okay? So when we look in the mathematical section of intersect, we can see there is all these intersection functions, brep and line, surface and line, mesh and ray, which just means mesh and line, curve and line and line. Then we have brep and plane, line and plane, plane and plane, mesh and plane, curve and plane, etc., okay? So all the mathematical intersections are referring to infinite objects, and then anything that's physical is they need to actually touch. So you'll see here, line and line is a mathematical function, but curve and curve is not. Because even if I had two lines and I actually want to find their physical intersection, they don't intersect, right? But mathematically, they do. Okay? So, what type of intersection do you think we're using in this example? It's either mathematical or physical. Right. So what type of geometry are we using? And then what other type? So let's go find brep, pipe, or vertical line, plane. Because that's going to be the type of intersection that we need. Cool? And guess what goes into B? And guess what goes into P? You already there? Excellent. Cool. Okay, so we've got our brep and plane intersection. That's generating a curve. You guys don't know this, but if we look in the physical section of intersection, you can see there is a component called surface split. It says split a surface with a bunch of curves. So what we can do is grab our surface and we can plug in the resulting curve output of a brep plane intersection. And what that'll do is if I just grab a panel, that will generate two surfaces, two trimmed surfaces. And I'll get into what trimmed means later, but that's effectively what we've done. Really? That's fine. Are you sure your angle is? Just make sure this angle is sensible.
Actually, I know what I've done.
Yeah, just. What was your question? So what that's done is it's generated two surfaces. So it doesn't remove. It obviously doesn't know which one we want to remove. So it's giving us two. So if we just quickly go and grab a list item, and we have a look at the first item of the surface, we can see that it is the one that we don't want. Okay. And we can also, so if we plug in the number 1 into that list item, it's going to give us the surface that we do want. Now, I can probably testify that you're never going to know exactly which item that is, because as I rotate this, there's a chance that it's going to be the wrong one. Okay? So I just want you to know that even though you might use the right number here with one set of parameters, it needs to be changed. So if your script starts breaking, it's probably because of this. So what I'm going to do is just plug in the number 1 into that. And we're going to make it big so that it's important, because big things are important. And we should end up with the surface. Cool? Okay. Okie dokie. We're going to do another type of intersection now. Let's draw. Okay, so we're almost there, guys, right? So we've got our shape that sort of forms this that little canopy extension, and now we need to make this wedged, okay? And the way we're going to do that is we could just generate more planes and keep slicing at this thing, but we can actually we can do another type of intersection because that's pretty much what this whole lesson's about, is parabolas and intersections. So another way that we can do intersections on shapes is if we generate curves. Like if I take this curve here, you don't need to follow along right now. Hey? Okay, that's cool. That all good, man. So if I take this curve, yeah, there are functions that allow us to project curves onto the surface. So under utilities, if I take my surface brep and I take my curve, I can project that curve onto the surface, generating that shape, right? Cool. So instead of using planes, we can use curves. And remember, what did we do with this surface split? What did we need to actually split the surface? A curve, right? So if we basically generate a polyline that goes between, you can follow along now, except for Joe's, seeing as he crashed his script. By the way, a good idea within the very first two components that you place is to save, because Grasshopper doesn't auto-save unsaved scripts, but it does auto-save saved scripts. So that's a good idea. So what we're going to do is merge our point over here, this point. Then we're going to merge our center point and then our third point, which should then, if we plug that merge into a polyline, it should be fucked. So the reason that's fucked is that the way merge works is merge really cares about this little address system here. So you can see this point is within a branch that is 0, 0, but our point over here is in a branch that is just 0. So when it merges them, it considers that what I'm telling it is, I want you to merge the two branches that are the same together, and the one branch that is different, keep that separate, okay? So just as a cheat's way out, well, not cheat, me cheating at teaching, so I don't have to explain this perfectly right now, is all we need to do is flatten the lists as they go into the merge, and that should then construct a nice polyline the way that we drag them in. There is another component that does this that makes you ignore using the flatten, but I think it's this one, entwine. Let's try that one out. If you use entwine, oh no, entwine's also doing the exact same thing. No, don't use entwine. Entwine's not what I thought. We want polyline. Merge and polyline with a flat. Cool? So you can see that's creating our nice curved wedge shape.
It's coming up with an error saying insufficient points for a polyline.
Did you flatten it? As in, see the merge? Are each of these flattened?
Oh, yeah.
It's fixed now? Excellent. Cool. Okay, so we've got our merge creating polyline. If we now take that over and we go grab a project, I know I grabbed project when I told you not to follow, but you can find project under curve utility. It's probably the only one that's confusing because it uses surfaces and it also uses curves. So you would think, oh, could you find that in the surface tab or could you find it in the curve tab? In this case, the result that it generates is a curve. So we'll assume that it's a curve component. We're going to plug our, you look excited. You're like,
I'm back to circle. I had to close
okay, man. Well, it's a good thing Logan's been literally following along with you because I'm sure he'll share his script with you. So then if I plug my polyline into project, then it will generate the curves that actually create that wedge. Yeah? And look at this. Look, they're doing exactly what I expected them to do. As they tend towards this point here, they actually touch that point. So all of these sort of like parent-child relationships that we've created are working to our favor right now. Cool. Okay. So then we've got a curve and we've got a surface here. Let's use surface split again, but this time we'll use the wedge. And I'm going to have a guess here and say when we use the list index to pick out the one that we want, we still want 1. Excellent. But for some of you, it might not be. Please consider that. And look, we've got a nice segment of a hyperbolic paraboloid. Are we meant to finish at 12?
Yeah.
We're almost done. I think. Huh? Pardon? Okay, so there's one more thing. What do you think that is?
You need to replicate the shape around.
Yeah. Yep. And seeing as today we introduced rotations, let's do a rotate. Shall we? Yeah? Okay. So, is everyone got this except for Joe? No?
I just couldn't see because can you zoom it in? What?
So what we've done is we've used the polyline on the project and then we've copied surface split and list item. And instead of using the old curve and the old surface, we've used the new surface to split and this new wedge curve. Man, if I learnt this stuff when I was learning Grasshopper, I'd probably not be in Sydney. I'd probably be in London or the US or somewhere like that. Seriously, the fact that you guys are learning this as most of you are bachelor students. I had to self-teach myself this in between. I started learning it in between my bachelor and my master's degree of architecture. And I spent 2 years teaching myself how to use it. No, I didn't even do it then. I actually started learning it halfway through my first year of my master's degree. So by the end of my master's degree, I had such measly skill to be the only person in Adelaide to know how to use this. I'm from Adelaide. and I got invited to work for a company. I didn't have to apply, right? You guys are learning this from someone who actually has made a whole bunch of mistakes and knows what you should be learning. You can go wherever you want with this shit. This is cool shit, okay? Companies are just learning about this stuff now. The fact that, you've got this sexy little wedge here and you know how to make it, there's power in this. There's a lot of power in this. No, I'm serious. Like the fact that you can do this. Ooh. Or this. Oh. This is cool stuff, okay? Because now that we need to rotate this thing, how many rotations do we need to do? As many as the segments we need to produce, right? And how many segments have I currently produced? I need 10. Because remember, we've dispatched it. We times it by 2, but we're dispatching, so we're getting rid of half. So if I times something by 2 and then halve it, what do I end up with? Straightforward question. The same thing I started with, right? So we need 10, okay? So if I need to rotate something incrementally 10 times in a circle, how many degrees do I need to end up with? I need to divide 360, right? Okay, so if I need to divide 360 by 10, can you guys think of a component that we've been working with that takes a number and divides it evenly by another number? Not divide curve. I said numbers, not curves. Can you think of... Range, exactly. Range takes a number and divides it evenly by another number. So if we take a range and we plug in good old 360 degrees, and we plug in the number 10 into that, we should get a nicely divided set of numbers. That's a weird one. I've never seen it do that before, but that's okay. We get a nice set of numbers, divide by 10. They go up to 360. Okay, one question. Can anyone intuitively see a problem with what we've just done?
Are we going to get done over by the mirror?
No.
Mirror's gone.
Mirror's okay. But it's a good thought. Always keep that in mind. Are you going to get done over by the mirror? No, because the reason I told you that was shit, a shit way of doing it, is because it is a shit way of doing it. Okay? It's shit. Remember that. Yes?
We're using 3 points along the line, but we're dividing by it.
No. Look at, okay, try this. If I take a curve and I rotate it 0 degrees, is it going to be the same? Okay, if I rotate a curve 360 degrees, is it going to be the same? Yeah. So can you see, I've rotated, the numbers that I've got go from 0 to 360. So that means the first and the last rotation are going to end up giving us the same result.
So we need to stop the final rotation.
Yes. Okay. So also, we can see here, one, I'll do it on the computer so that those people who are sick and not here can see. Hello, sick people.
And Beil is for expression.
Hi, Joe. How you doing? I hope it's not too late right now, future Joe. I know you're probably working with Logan's script right now, and you're just sort of like, no. We'll say hi to Yuen. I know hi Yuen. How you doing? The classes get well soon. Do you agree, class?
Yeah.
Okay, good. Yeah. You have to force people to say that nowadays. Sorry, UN. Sorry for singling you out. Okay. So if we look, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need 10 segments. And how many rotations have I produced?
11.
Yeah, I've produced 11. So, even though I've plugged in 10, what that's doing is it's actually creating 10 equal segments, right? So there's going to be one extra number. Fortunately, that one extra number is the number that we don't want. It's 360 degrees. So what we can do is we can get rid of that and we'll have the exact number of rotations that we need without any duplicates. What index do we want to get rid of? 9. Are you sure? You want to get rid of 324?
This is the 10th index.
We want index 10.
No, you want to get rid of index 0. First one.
We could get rid of index 0, or we could also get rid of what? And I want you to answer in a really clever way. A way that wouldn't matter how many I've used. I could have used 6, I could have used 1,000. What index do I want to get rid of? -1, okay? I'm gonna bring this up over and over and over again. The last item in the list is always, it's better to think of that as -1 instead of 10, okay? So let's get, and yeah, you're right, we could get rid of 0. That is a correct answer as well. So you can choose 0 or -1. The point is, we are going to go grab col index. We're going to plug our range list into that, and your choice, either 0 or -1 as the index to remove. I quite like 0. 0 is a really nice number. We can thank the Indians and the Arabians for that number. Did you know it didn't exist in many other cultures? And that's why they couldn't advance? Because 0 is a very powerful number. It's very powerful. Once they got it, through trade, things started to change. Yeah. It's funny how those tiny little discoveries can basically allow so many more technologies and discoveries and ways of thinking to expand. For example, China was incredibly advanced. They had sailing ships well before the rest of the world. They had black powder and explosives way before the rest of the world did. So, swashbuckling movies with pirates, right? And the way the English basically took over half the world because of their sailing ships and their gunpowder, hence why we've got Australia, and hence why there's America. China could have done that hundreds of years prior, but they didn't. And do you know why?
They didn't have glass.
Yeah, they didn't have glass.
Glass.
Yeah, yeah. They didn't have glass. Glass is such an important thing for understanding the planets and understanding navigation, nautical navigation. I'm sure someone has been watching QI. Okay, so we've got our our coloured index. We're going to use these numbers now to rotate our segment. So let's just pull all of this stuff all the way to the end, because we're going to use that to rotate. Okay, So what did we do before with rotate? We had a piece of geometry. We needed an angle. So if we plug in our cold indexes into the A, now just remember we divided 360 watt. What's the unit of, no, 360,
Not degrees, the other one.
yeah, degrees.
Oh, it was degrees.
360 is a full circle in degrees, not radians. So we need to make sure that the A input is in degrees. And all we have to do is hide our original surface that we've been rotating. And we result in the most beautiful hyperbolic paraboloid pavilion ever. And the beauty of this now is because we've set the way the parabola generates, like so the midpoint is the center of the circle, yeah? That means that it's tangential at the midpoint. So we've kind of been generating these like circus tent like hyperbolic paraboloids in the past, like where the midpoint is kind of a little kink in this system. This way of generating the hyperbolic paraboloid guarantees you get this nice, beautiful tangential curve in the middle, and it's just so, oh, look at it. It just satisfies all the OCD aspects of my mind. Yeah?
We wanted to make it more, because his curves, some of them are really pointy at the top. Would you just go to the center point of the circle and put like a Z factor and a number slider?
What do you mean?
To pull this point more upwards to make
If you want to pull it up,
Yeah.
then instead of pushing the point down, push it up. But just remember, so we've got all these parameters now that are the parents in the chain. So like as I pull, so this point here is for parabola B. So as I pull that up or down, that's going to change the strength of that parabola and therefore affect multiple aspects. So like the curve that's generated here is actually resulting from the actual curve of the parabola. So when I change that, it's not going to change the angle of the plane and it's going to get sharper, yeah? And as I make this less and less and less to the point where it's literally a straight line, or to the point where if I were to go, let's say, negative, that's when things start getting trippy because we start generating hyperbolic paraboloids that Candela actually never constructed. Like this is a hyperbolic paraboloid inverted, yeah? So actually, I'm not sure if he actually did anything like this. Kind of looks like a orange juice maker. Yeah.
In some of these geometries, they're kind of pointy at the exterior, like the top.
Pointy.
Yeah, like they're just triangular instead of like round.
Oh, you mean this exterior?
Yeah.
That means he's probably actually using what we originally did.
Right.
Yeah. And the interesting thing is what we originally did with the 4-point surface, that 4-point surface actually exists somewhere on this hyperbolic paraboloid. Yeah? It's just good luck finding it. But yeah, there's this. I know, like, yes, some of you, this isn't going to be relative to you. So if you can recognize that this doesn't match how your Candela form works, that's okay. Just mention that, but then do what we've done this week, okay? Because it's important to learn that.
Could you insert, like, how you use the plane?
Yeah. It doesn't. You can actually create a wedge and cut the other side. But then the cool thing about the plane method cutting it means that everything on that face is planar. And so, yes, I know I said parabolas are fucked, right? But if I can make something at least planar, that means I could laser cut it. Or I could give a flat plan, elevation plan, to a timber manufacturer, and they could produce the nice, a nice like end cap timber face to that element, and they don't have to fuck around with like something that's deep, like changing in direction. So just be mindful of that. Especially, you're going to have to use this geometry for the next few assignments.
So as long as we recognise that it's not our one,
Yeah.
but the kind of method.
Yes.
Okay.
Yeah. So, and this is why I don't think giving out candela forms at the beginning is a good idea, because actually some of you have been you should have been doing this for the first few assignments, when in fact you didn't know how. And now that I've taught you this, the rest of you don't actually have to do this to get your candela form. So we might as well just be doing this, right? Like whatever's in class.
Yeah, I've sort of not really been doing like that.
It's fine.
Just been quite happy to produce the shadows.
Yeah. So it's all good. Do we actually have to make anything? Huh? You're missing one.
Yeah. Like it doesn't go, it doesn't return.
Ah, you're doing it in radians, not degrees.
Oh, but
So I've got a circle with 2 points.
Excellent, man. Good. You got back there without me. That's good. Hello. I think I know the answer to this, but I'm just double checking. So don't give me a face like you should know this, Andrew. This is me double checking, okay? There's no model this week. Good, I like that face. It's a good face. Okay, so I just want to prove to you one more thing. What time is it? Look, we killed it. We absolutely killed it. Like, do you remember the nightmare that was the finger joint? Today is so much easier. We should have done this 2 weeks ago. Would have been so happy. I would actually have a bigger class right now, because I wouldn't have had all those people drop out. Being like, oh, this is fucked. These guys are insane. Okay, so what this means is, now we can basically stop. You can stop following along. I'm just going to show you a few things. Okay, if I generate a 4-point surface that actually makes that hyperbolic paraboloid, and as I mentioned earlier, it exists on a weird plane, I think. No, let's do this. So, ooh, yeah, it's kind of working. I'll try to get it as close as possible. Okay, so if I take this surface and actually start looking at its topology, and I know we haven't really been talking about topology, but it becomes really important in a few more assignments. Topology is kind of like it's a maths term, and it's talking about the way things are structured inherently. So, for example, has anyone seen Good Will Hunting?
Yeah.
Everyone seen it? No? Okay, if you want to watch a film that doesn't have Robin Williams like trying to make you laugh at every moment as you watch it, then Good Will Hunting is one of those films. He's not trying to make you laugh. It's interesting. If anything, it was his attempt to like get away from comedy and actually do serious acting and stop being referred to as Mork from Ork. Well, in Good Will Hunting, there's a problem that's presented, and it's actually quite an easy one, but it's referring to topologies. So if I drew this shape as a connection of nodes, so here's some nodes, yeah? And I then draw this shape, are they similar? Why? How are they similar?
Common set point.
So they are similar in topology, okay? So we can see that this one has a center point that is a hub that connects 4 points outside of it, yeah? At the same time, this one has a center point that connects 4 points outside of it. So they are topologically similar. And I know a few people get mixed up when I say topology and they think I'm saying topography. Is everyone thinking I'm saying topography? Everyone know what topography is? You know the topographic contours that you get in sites, you know, that show the horizontal contour lines, the topography. Topography is actually, it's similar to topology. It's referring to the like the topological way things are connected, but in geography, okay? I'm losing people, I can see that. Okay, so, this is good. It's good that we've got this extra 30 minutes. Do it. So, this is going to be one of those repeating things that I'm going to say a lot from now on. Very similar to what is the last item in a list. What index is the last item in a list?
-1.
Right, I'm going to keep saying that, and I'm also going to keep saying this next one. All surfaces have 4 sides. So, if this is a surface, how many sides does it have?
4.
Right. If this is a surface, how many sides does it have?
4.
Are you sure?
No, you said yes.
Yes, it has 4. Good. You're listening to me. Good. But also, you know, don't listen to everything I say. I might be an idiot. Okay? How many sides does it seem like it has? 3. Okay. How many sides does this surface have?
4.
Okay. How many does it seem like it has?
6.
6. Okay. Okay. So surfaces are mathematically produced. Okay. That means, remember that when I draw a line in a NURBS program, there is a maths function right, whatever, that's actually producing that curve, yeah? And the way NURBS surfaces are produced, there is a topology that goes in what we would think of in an XY plane as X and Y, but when we refer to them in 3D space, any space that is different to world, we're going to refer to them now as U and V. Okay? Does anyone use 3ds Max or SketchUp? 3ds Max, have you ever seen UV mapping in there? Yeah? Or does it refer to UV mapping in SketchUp? I don't use it enough. No? See, this is why 3ds Max is so much better, because it actually teaches people maths without them realizing. Okay? You know UV mapping is what you need to use, but you don't actually know what UV stands for, right? Yeah. Right, okay. So U and V is effectively the Einstein warped space in 3D that refers to X and Y, okay? So if I were to take this piece of paper and put it at, we're gonna say from now on, the reality of universe, of the whole universe, is centered on this whiteboard, I know. What circumstances? How coincidental that the center of the universe is actually going to be on my whiteboard in this class, right? This is the center of the universe, yeah? And its point is going to be as X, Y, and Z as 0, 0, 0. This is the center of the universe. It's there must be a reason why it's here. It must be me. Or does anyone here think they're the center of the universe? No? Okay, excellent, good. Okay, so if I were to put a piece of paper relative to that point, then I hope this drawing doesn't matter. This piece of paper, if I put a point on it, that point is going to be the same on the piece of paper as it is in the universe coordinates, right? But the instant I move the paper, its XYZ has changed, yeah? But in relative terms to the paper, we can think of the point's coordinate as UVW, okay? Cool? It's simple. So basically, as long as you've got something that has a coordinate and it's not relative to the center of your model, then we're going to think of it as UVW, okay? So let's get back to four-sided surfaces. What a NURBS surface does is it defines a maths function for all the curves that make up that surface in the U direction, and it defines the same maths-based curves or control points in the V direction, yeah? U and V, yeah? So no matter what, U and V is got to have an opposite side. U has to be also U up here, and V has to be V on the opposite side. So no matter what, you're always going to have four sides because you've got two directions that generate that surface. So I hear silent questions, but what about triangles? It doesn't, the triangle doesn't have a fourth side. It does. It has a fourth side. So if I say this is U and this side is V, so therefore where's the opposite side of V? We'll say the opposite side is here. Where then is the opposite side of U? The point, which means if this is 10 long, 10, how long is the U on the opposite side? 0. It's still a side, it still exists, yeah? So if I draw that same grid, that grid would look like this. Cool? Okay, so my surface, how long have we got? Oh, plenty of time. Okay, so there's one other thing that we can do to surfaces to make them seem like they've got less or more than four sides. And we've seen it today. What can you do to a surface to make it have more or less than four sides? we can trim them. Okay? So this shape here, if it was a surface, it's actually a four-sided surface, and we're just seeing the trimmed sides of it, but mathematically, it's still got four sides. Okay? So, what does this mean? This four-pointed surface no matter how long it is, we'll make it like this. Where is its U? Let's say it's U's here, so where's its opposite U? I wish U and V looked different. Because then when I do V, I have to really make sure that V looks different, right? Because V almost looks the same. So then V on the opposite here is here, yeah? So that means if I start drawing this grid, it's going to start looking like this, right? But with our hyperbolic paraboloid that we've made with parabolas, we made a surface in plan that looked like this, yeah? Let's just draw a little bit of it in 3D, yeah? So if I were to start getting its U's here, its V is here, which means if I were to draw this UV grid, instead of it being this sort of like diagrid, it ends up producing these nice little parallel parabolas, okay? So I'm going to show you now. And this is, like, sometimes the way you make your surface is actually going to determine what you can actually do with it further down the line. So this surface here, if I break that into its UV components, check it out, U and V, right? Divisions along U and divisions along V, giving us this grid of points. If I actually start to connect those points up, and let's just give them a thickness so that they're easier to see. Ignore, like, this is using some plugins and hide. So I'm going to do the direction that goes along U in white, and then I'm going to do some data management trickery here to generate the lines that go in V, but we're going to put them in black. So there we go, there's our topology that matches, like it shows us the grid of the U and V for that surface. But if I use that same process on our lofted hyperbolic paraboloid, I'm going to copy this instead of replacing it. Then, look, we get this much nicer grid and also perpendicular to itself topology, and we also know these are all parabolas, right? Because of the topology, how that works. Does that make sense? Okay, cool. So just remember, though, that this trimmed surface here, even though it looks like it's three-sided, we can see with the panel, it's telling us it's trimmed, okay? So we know that there's more beyond the edges than what meets the eye. And there is this nice little utility here called untrim, which will actually give us the original surface. So if I just plug that into its own surface component now, come on. Let's try extrude it. That will actually bring our surface back. Okay? So even though we've trimmed it, we haven't actually lost that original surface topology. So if I then plug, and we'll see that in the next few weeks as to why it's good and sometimes why it's bad. So if I plug in my trim now into this surface, damn, that's actually not a good example, but yes, it's going to follow that topology. Cool? Does that make sense? So how many sides does the surface have? And how many, is it ever going to be more or less? Huh? No, it can't. It's always four-sided. Always. Every surface every mathematical NURB surface is four-sided. Even if it seems like it's two-sided, it's four-sided. Trimming just it reduces how much of the surface you can see, but it doesn't change how many sides it's got. So if I drew Earth, this is good. I like this. This is our last 15 minutes. I love this. This is a good example. If I drew Earth as a surface, how many edges does it have? How many sides does it have? 4, right? How can you think of any way that we represent Earth with 4 sides? Can you think of any don't just say flat. Can we think of any way that we represent Earth with 4 sides? How many sides does a circle have?
4.
No. If you had a surface that was a circle, yes, I would agree with you. But circles are different to surfaces. Let me jog your memory. Hello, Internet. Please connect.
So you like unwrap the sphere and you show a flat version of it?
Can you think of any unwrapped sphere that we use all the time? I'm not gonna be like, I can't be any more obvious than what I am being right now. So the way that we map Earth on Google Maps is taking a sphere and I'm surprised that we can only see this much. How can I can't zoom out anymore? True size of is a better example. This is fun. This is really fun. Okay, so here is our nice little, this is like a rectangular, four-sided view of Earth, yeah? A sphere, right? But if I were to say, okay, think of the way that we worked with the triangle. If I said the Earth is a four-sided surface, then how wide is the U of that surface on the bottom? As it gets to the bottom, it gets infinitely small, right? Because it becomes 0 at the point. And then as it gets to the north point, it's going to be 0 as well, yeah? So that means when we unwrap Earth to a four-sided object, the top and the bottom are actually starting to represent something that becomes infinite, yeah? Which means that if I look at Greenland, what that's actually doing is it's getting wider and wider as it gets closer to an infinitely thin point, yeah? Which means if I pull Greenland away from Greenland and actually show you how big it is relative to something that's actually represented by its actual dimension, Greenland is quite small, okay?
So it doesn't even show that it's really small.
On the map, yes. And now this is why atlases, and when I say atlases, books. Do you remember atlases when they were books? Yeah? Most of those actually showed you the real size of the thing. Because when you go and look at Australia in an atlas, you're looking at Australia relative to itself, as close as it is to its own projection. But then when you look at the full map of Earth, there has to be some distortion. And so we can show Australia compared to Greenland, and as you can see, Australia begins to only warp just a little bit as we put that over Greenland, but the most fun one is Antarctica, because Antarctica is on that infinite point. So if I bring up Antarctica, Antarctica looks like it's this giant land mass that goes around the whole strip of the Earth, which is it is topologically correct, but it's actually only that big. Okay? And we're going to get into this soon, okay? Because we're going to do some functions that actually use these concepts. But isn't this interesting? You didn't even realize this stuff. And you use it every day. Yeah? Earth is 3D. It's like, there's all these flat earthers. No one says, here's a flat earther. There's so much proof as to why Earth is 3D. Like, you can use maths, you can use science, like all this stuff is proof. We can prove that Earth is 3D in using Grasshopper. Yeah. Like, Antarctica is growing or shrinking?
Like a year ago, they said it like grown.
Grown?
Yeah, because the ice mass.
No. If we consider Antarctica a land mass with ice on it, then if the ice was shrinking, then it won't grow. It's just we're going to see the land mass more easily.
It's the ice.
The ice is shrinking.
Yeah, this is the winter time.
Oh, yeah, because it's winter. Yeah.
Presented as they presented as like enormous.
Oh, okay. Yeah, that's what weather is. Weather's random. I don't want to get into the politics of global warming, but we'll because that's something that hasn't, not everyone's 100% on that one. Not everyone's 99.8% on that. That 0.8% of the world still think the world's flat. But we can all agree on that one, right? Yeah. No, let's not get into weather politics, because I'm going to get myself in trouble. Cool. That's fun. That was a pretty chill lesson. And as well, you guys don't have to actually produce a model this week. Excellent. Which means your renders have to be amazing. Cool. Okay, so next week we're going to get back into making shapes. Like with physical shapes.